All right, let's dive into one of the most exciting ideas in all of artificial intelligence, reinforcement learning. We're talking about the science of teaching a machine, but not with a list of instructions. No, this is about teaching it through pure trial and error, kind of like how you'd teach a dog to fetch.
So let me ask you this. How would you teach a computer to master a game like chess if you couldn't give it any rules or strategies? You don't tell it what a good move is, you just let it play, over and over and over again, learning from what happens. Well, that's the exact puzzle that reinforcement learning was built to solve.
You know, this whole idea of learning from consequences, it's not new, not at all. It actually comes from a principle in psychology that's more than a century old, called the law of effect. A psychologist named Edward Thorndike noticed something pretty simple. Actions that lead to good things tend to be repeated, and actions that lead to bad things, well, they don't. This basic intuitive concept is the absolute bedrock of modern reinforcement learning. So what is it really? Okay, formally, reinforcement learning is where an AI, we call it an agent, learns how to make decisions by just trying stuff out. It takes actions in some kind of environment, and it has only one goal: get the biggest total reward it can over time. The key thing to remember here is that nobody ever tells it what to do. It has to discover the best moves all by itself. Now, this learning process isn't just chaos. It happens inside a constant feedback loop. You can almost think of it like a conversation, a back and forth between our two main players, the agent, who's doing the learning, and the environment it's living in. And that conversation always follows the same 4 steps over and over. First, the agent looks around and observes the current situation, or what we call the state. Step 2, based on that state, it decides to do something. It takes an action. Third, the environment reacts and it gives the agent a reward. This is just a number, basically saying good move or bad move. And finally, the agent finds itself in a new state. This cycle, state, action, reward, new state, just keeps repeating, and that's where all the magic, all the learning happens. So the agent, that's our star player. It's the learner, the decision maker. This could be an AI playing a video game, a robot trying to find its way out of a maze, or even an algorithm that's learning how to trade stocks. It's the one making the choices.
And the environment? Well, that's pretty much everything else. It's the world the agent interacts with but can't really change. For a chess AI, the environment is the board, the pieces, and what its opponent does. For a self-driving car, the environment is the road, all the other cars, and, the laws of physics.
Which brings us to what is maybe the most important part of this whole thing: the reward. It's just a number, a simple signal that tells the agent how it's doing. A positive number is like a treat, a negative one is a penalty. And here's the crucial bit. The reward signal defines the goal. The agent's entire existence is dedicated to making choices that will get it the biggest pile of these reward points in the long run. Okay, but this constant hunt for rewards leads to a really fundamental problem for any learning agent. At any given moment, it has to make a choice between 2 very different strategies. Should it stick with what it already knows works, or should it try something new? This is the classic dilemma of exploration versus exploitation. Exploitation is all about using your best-known strategy. Think of it like this. You go to your favorite restaurant. You know the food's good, you know you'll like it, it's a safe bet. Exploration, on the other hand, is about trying something new. You could try that new place that just opened up down the street. It might be awful. Or it could become your new favorite. You have to explore to find better things, but you have to exploit to get the benefit of what you've already found. And this table here really shows why that balance is so important. An agent that's greedy, one that only ever exploits, only ever goes to its favorite restaurant. It gets better fast at the beginning, but it usually gets stuck in a rut, never realizing there's a much better option out there. But an agent that spends just a little bit of its time exploring, it learns slower at first, sure, but it will almost always end up with way better results in the long run. It might have a few bad meals along the way, but it's much more likely to find the absolute best restaurant in town.
So how does the agent actually make these decisions? How does it balance this whole explore-exploit thing? Well, we can kind of peek inside its brain, which has 2 main parts that it's always trying to improve: its policy and its value function. The policy is basically the agent's game plan. It's the rule book that tells it what to do in any situation. If my opponent does this, then I'll do that. As the agent keeps learning, it's constantly tweaking and updating this policy to make better and better choices.
The value function is a little different. It's how the agent figures out how good a particular situation is. It's a prediction of all the future rewards it thinks it can get from that point forward.
So a state where the high value is a really good place to be. You can think of it as a treasure map. The map tells the agent which spots on the board are close to the treasure, and the agent uses that map to write its policy, its rule book. The rule just becomes, always try to move towards the spots with the highest value.
Okay, so that's the theory. But does this simple little loop of trial, error, and reward, does it actually work in the real world? The answer is a definite yes, and the results are pretty incredible, taking us from board games all the way to complex robotics.
One of the earliest and still one of the most jaw-dropping examples was an AI called TD Gammon. It learned to play the game of backgammon, which is super complex, not by studying human players, but just by playing against itself.
Now, get this. TD Gammon started from scratch. Zero knowledge of the game. Nobody programmed in any strategies. It just played against a copy of itself around 300,000 times. And through that process, just learning from its wins and losses, it discovered strategies that human experts had never even seen before. And in the end, it reached the same skill level as the best human players on the entire planet.
But reinforcement learning isn't just for games on a board. It's also amazingly powerful for solving really tricky physical control problems. Take the acrobat, for example. So, the acrobat is like a simple robot gymnast on a high bar. The catch is, it can only push off from its waist, not from its hands. The goal is to get its feet to swing all the way up over the bar. And this is an incredibly hard problem to solve. But through pure trial and error, the reinforcement learning agent figures out this really complex, non-obvious sequence of moves to pump energy and momentum into its swing to get all the way up there. It learns a sophisticated physical skill totally on its own.
And all of this brings us back to one final, really interesting question. The power of this kind of learning is all in that simple reward signal. The agent will learn to do whatever it takes to maximize that signal. So, if you were the one designing an AI that learns this way, what goal would you give it? What reward would you set? It really makes you think, doesn't it? Thanks for joining me.